The simulate process, design studies and optimization. Last week when I did the webinar on BMX, I did more of behavioral modeling and optimization over there. This would be more or less structural and modal optimization. Next time I do a webinar, I'll be talking more thermal analysis, connections between assemblies, interfaces, and stuff like that. For this week, I have these. Rosalinda is going to go ahead and start a little poll. Let's get through that and we'll get started.
Alrighty then, here we go. We have 2 more. Here's the last one, and that'll do it. It's all yours, Sukumar.
Alright guys, so last time we talked about Creo Simulate. We discussed all the new enhancements in Creo, right? This time I want to go ahead and do it more of a teaching session where we talk about what the process is, what are design studies, how we can use them, some workarounds to play with design studies, and optimization and how it works. All right. So I'm going to get started with process first. Let's kill this. So what I have here is a little part. Okay. I'm going to go ahead and get rid of what I've already done. In a second, and then we'll get started. So let me get rid of these. Also get rid of all the loads and constraints. I should have at the beginning, I forgot. So alright, so basically we have a part, the process involves material assignment. So you go ahead, click on the material assignment box, click more on the material, and you can go ahead and pick whatever material you want from this list. Now a lot of people have been asking me as to, hey, you know, are these the only material? Can we download something? Yes, there are a lot of free downloads available. I can ask Rosalinda to shoot you a link with a lot of these free downloads of materials. What you can also do with respect to materials is you can use the existing one, make a copy of it. Okay, so here I'm going to make a copy of steel. I'm going to double click on that. You see you have all your standard properties, isn't it? What you can also do right here is you can get rid of the Young's modulus, for example. Right click, you can insert a function or you can insert a parameter. So let's say a parameter. We don't have any, so I'm going to go real quick and create one. That was tacky. So let me go tools, parameters, and let's create Young's modulus, let's say 200,000. We'll also create one for load and say 10,000, right? And let's say we will also create another thing for say load 1 and say 5,000. All right, so we can create these parameters, and then we can go back to our material make a copy of that. I'm going to double click on it. And here, I can right click, insert a parameter, and pick E. Now, what is the advantage of this E? Now, let's say, for example, you're using stainless steel, and then you want to go ahead and say, hey, what happens if I want to use a different grade of steel? So you can vary the Young's modulus, and you can plot stress strain curves, or say, for example, your displacement to your Young's modulus curve. You can see which type of steel gives you the best possible result. Okay, you can also do that. Now, once we assign our material, second thing we're going to try and do here is apply loads. So I'm going to use bearing loads right here. So pick a surface, and let's say 10,000 on this one and 5,000 on this one. Even here, what I could do is I can insert a parameter and pick load 1. I can go here, insert a parameter, and I can pick load. See that? And you can also do times 2 or times 3, so on and so forth. So I have a bearing load right there. Similarly, I'm going to apply more bearing loads real quick. So let me go ahead and do that. So I'm putting 1,000 here and a 500 smaller loads, and then I'm going to use the parameter load. Okay. Now, once I do that, you want to also go ahead and say constrain the surfaces. Okay. Now, when you constrain the surface, let's say I'm going to put a nut, like tighten the knot, right? So one way of doing it is to constrain the whole surface. Another way to do it is to basically go ahead and create a little surface region. So I'm going to create a surface region, which is a sketch on this surface. Now I'm going to use those as references so I can create them real quick, and then stick in a circle. I'll say OK, pick the surface, and say done. Now you see one of the limitations is that you cannot have multiple closed loops within a surface region. So what I'm going to do is I'm going to cancel out, just for this purpose, I'm going to create a volume region. Pick the same surface, do the exact same thing, and you see that the volume region will let you do what I was trying to do, where I want to divide the surface into multiple closed loops. See that? 3 of them, and I'm able to divide it. So that is why if you use a volume region, you can do all of it at once, which makes to less work. Now I want to go ahead and constrain the top surface where the bolt head interacts with the part. So I'm going to fully constrain that, and I'm also going to say that this part is symmetric, so I use mirror symmetry and pick that surface. Alright? Now that's one thing. Next thing is when you run the analysis, I've done 2 passes right here and I explain what these are. So I'm going to go File, New Static. In here, note that you can choose multi-pass or a single pass or a quick check. Okay. Now, what is the difference between multi-pass and single pass? Let's get through the passes first, and then we'll discuss the differences between them. Okay. As of now, I'm going to choose a single pass. Now you see that if you have an assembly, you can do localized mesh refinement. If you do contact analysis, you can check for contact force. And if there is any, interference, then you can check the press fit and ignore the interference over there as a interpenetration. Also in the advanced control, you can see that you can use the advanced control, select a certain edge or a surface, right? So you can see points, edges, volumes, components. So I'm going to pick a surface and say, you know what, the maximum stress error is 8, but the local stress error over here, I want it to be 10. So if I know there is singularity, then I can choose to ignore it. Okay, so I can do these things with the advanced control. In the output, you see that you have stresses, rotations, reactions. There is something called plotting grid. Now, what is a plotting grid? Let me just use Paint, which is my favorite tool. I can show you guys how it works. Now, let's say we have a plate and we have a hole. All right. Now, ProEngineer uses P-type FEA. P as in parametric. Okay. Now, in a P-type FEA, you can create larger elements to solve for your answer. All right. Now, similarly, in an H-type FEA, if you had the same plate with a hole, you would have to create much smaller elements. Now, why is that so? The reason you would have to do much smaller elements in H-type FEA is to avoid something called a discontinuity or overlap between the element edge and the boundary. Now, we can see that the boundary is right here, right? This is the geometric boundary, and you can see the shape of it is not straight. Most of the softwares which use H-type FEA, including ProEngineer, the H-type FEA has a limitation of the element edges not being of higher order. For example, a straight line is y equal to mx plus c. A curve would be like, say, a second order equation. A cubic curve would be a little more complex than that, right? Now, what will happen if you use a straight line to mesh this curved surface? You will have an error over here. To avoid that error, you will create smaller elements to match that boundary. You're making the error smaller, you're not eliminating it. Okay? In P-type FEA, the element edges order could go from 1 to 9. Okay, so it could be a 9th order polynomial curve which can match pretty much most of your geometric boundaries of parts, right? Now, another limitation of H-type FEA is that wherever these element edges meet, those points are called nodal points. Okay, so if you want an answer over here, you would get an interpolation of all these answers, or you just refine the mesh and create smaller elements. In P-type FEA, you get same accuracy because there is something called plotting grid. A plotting grid, when the value is 4, it will not only calculate the answer at the nodal points right here, but also at 4 locations along the element edge. Like that. It kind of gives you a mesh. See what I'm saying? Kind of gives you a mesh within a mesh to get you a much more accurate solution. All right. Now this plotting grid, which is number 4, what we saw right now, we saw that to be number 4. That implies there are solution is calculated here and here, but also along 4 points. Okay. So the typical value of plotting grid is 4. Some people like to increase it to 5, 6, 7, whatever you want. Now personally, I prefer to leave it like that and change or refine the mesh locally. Now why do I want to do that? if you change the plotting grid, you're not changing the plotting grid for a certain area. You're changing the plotting grid for the entire mesh. Now that could increase the solution time. If I say I want more local results over here, I will just create a surface region over there, and then I can refine the mesh. And I'll show you an example of that. Okay, so now let's go ahead and create a mesh. So here's the mesh. You can see the element over here, if it's say larger, for example right here, the elements are larger, right? So what I can do right now is I can go create a surface region or a volume region per se on that surface, and let's say I want to create a box. Alright. Now once I create that, I want you to map it to that. You can see how that surface region is shown right there. Now when you do an auto gem, you can see the box has much refined mesh. Instead of having bigger ones, you get smaller ones. Now there are different ways of refining a mesh. If I go ahead and make a block real quick and show it to you. So let's just go create a box. So here's a little block. Let's get into Simulate. First things first, let's apply our material property real quick. And then let's play with the mesh. So you say auto gem, you can see it creates these meshes for you. Alright? Now, what you can do is you can go to control and say maximum element size. So I want the maximum element size over here and here to be 20 inches. See that? And now you can create the mesh. You can see that you have already refined it. Right? That's one way of doing it. I'm going to go ahead and delete that mesh control. Next, edge length by curvature. You have minimum edge length. You can isolate certain elements for exclusion. You can create a hard point or a hard curve. You can say, hey, you know what? I want to pick a point over there, pick a point over there. So I'm doing that. Forgot to press control. So I created those 4 points and do an auto gem again. So you can see how those 4 points become nodal points. Okay. Just trying to show you different ways of creating the same mesh or kind of refining and playing with it. You can also create a hard curve where you can go ahead and select a curve. So let's go ahead, sketch something real quick, and let's say we do that. All right. So let's say if we can use this as a hard curve, there you go. Say OK, and then create a mesh. So you can see how it uses those curve boundaries also. Okay, let me show you a couple of different ways of doing this, and then we can go ahead and continue. So I'm going to delete all those. Now you can also say edge distribution. I can say I want to pick 1, 2, 3, 4 edges, and I want at least 4 nodes on each of them. So you can go ahead and create that. So you can see how you can have 1, 2, 3, 4 nodes on each of them. Right? So you can do that also. So you see that you can create prismatic elements, thin solid, you can also do a map mesh, and we'll talk about these two. We already spoke about most of them in the last webinar also. Alright, so here when you run the analysis, note that I'm running a static analysis. I want to go ahead and set my directory, working directory. So you can see just simple static analysis, and we'll look at the result for that. All right, let's look at displacement. So you can look at displacement. Now, going to also kind of show you the simulate results file right here. Notice that in a single pass analysis, ProEngineer runs actually two passes. I'm sorry, I called it ProEngineer's Creo. So in the first pass, the maximum edge order of the elements is 3. Okay, so we are using cubic curves to map the geometric boundary. Now it gets a value of all the stresses along each element edge, and then it runs another pass at element edge order 7. Now it need not be 7, it could be 8 or 9 depending on how complex your part is, right? Now it will compare the two passes and give you a result when the stress value should be within a certain percentage. So notice that the stress value is within 1%, which is pretty good. Now you can look at the result for it. Now you can see the maximum displacement magnitude is 1.13 e power minus 1. So it's a 0.113. Okay, and you can also see von Mises stress is 514. Now I run a multi-pass analysis. In here, notice that I'm going to say multi-pass. My polynomial order is going from 1 to 9. All right, and you see the percentage of convergence that I'm using is 5. So here I'm actually dictating the allowable error in the model, and also I can choose what gets compared. Say for example, in the first pass the element edge order is 1 and our stress value is von Mises stress is 100. Now it runs another analysis at element edge order 2 in the second pass. It compares the difference between stress in the first pass and stress in the second pass and sees if it is within the 5% of convergence, 5%. If it's not, then it's going to bump up the polynomial order of the edge and go to a higher value. And then it will compare pass number 3 to pass number 2, so on and so forth. As to what get compared is also controlled by the user by selecting measures. See, I've selected displacement, von Mises stress. I can pick a bunch of them by pressing control and say, okay, I have 4 measures selected. All right. Now, if we look at the results for this, you can see our area of concern was displacement magnitude. I'm going to also get the comparison for this. So you can see maximum bending is maximum displacement is 0.117. It's 0.113, which is pretty close, right? You can also see we were concerned with this, right? So a single pass has pretty much allowable convergence of 10%. With a multi-pass, you can basically go ahead and cover change that allowable convergence to 5%. Typically, most people who use Mechanica stick to 4 to 5%, unless it's a part that you're going to run optimization on and you're really concerned about it. You would go ahead and run it at 3 or 2% also if you want to. Okay. Now, this was kind of giving you an overview of all the buttons inside, kind of tell you what happens when you click on each of them. Okay. So, and also a difference between a single pass and a multi-pass. So why are we using a single pass? When should I use a single pass? Let's say I'm running a complicated FEA analysis. I am going to set up a bunch of different loads acting at different time steps. Now, I don't know if I set everything up right. So as a quick check, we can use a quick pass or the single pass to kind of run it really quickly, get to see the animation and the displacement values or the stress values and see if we have defined everything correctly. Once we decide that, okay, everything that we defined is correct, then we can set more stricter criteria and run a more stricter analysis, like say a multi-pass analysis. Okay. Now, next thing I'm going to talk to you guys about is design studies and optimization. So let's look at design studies. So I'm going to use a tuning fork. Now you can do structural optimization. You can also do modal optimization. The picks and clicks are the exact same. So I'm going to use something simple, like say a modal analysis of a tuning fork. Okay. So how do we find out what is the natural frequency of this tuning fork? Because we did structural analysis last time, I wanted to go ahead and do something with modal. Now, we are applying a constraint, see that, on that surface and say everything is fixed, right? Now that's where we hold it. So I want to fine tune this tuning fork. So before that, I go analysis, I'm going to run a modal analysis. Notice it's a constraint modal analysis. And I'm interested in modes 1 through 4. You can also say, hey, you know what? This machine is going to be working on the bridge. The bridge's natural frequency lies between 500 and 10,000. Let me find out if there are any natural frequencies of this particular part within that range. So I can say, hey, find me natural frequency between 500 and 1000. So it's going to find out the natural frequencies and tell you, hey, there is a possibility of your machine's natural frequency matching with the bridge's natural frequency. If that happens, then everything's going to vibrate because of resonance, and then the bridge might collapse. So you can find it within a range, or you can go, hey, just tell me what are the natural frequencies, the first 4 natural frequencies. All right, so you can do that. Now let me set my working directory real quick, and I can go ahead and do this natural frequency analysis. So here, I'm going to look at the result for it. You see that we have 4 natural frequency, 197, 204, 229, and 254. All right. Those are the 4 natural frequencies of the tuning fork. Now, why are natural frequencies important? What does the modal analysis give us? Modal analysis gives us the natural frequency and also the mode shape. What is a mode shape? It is the possibility of, let's say, how is the part going to vibrate or displace as the natural frequencies match. So if the first natural frequency of this tuning fork matches with something else, this is what we get. Okay, that's how it's going to vibrate. Now I can copy this and say, what happens if the second natural frequency, which is 204 Hertz, matches? So you can see how it's going to vibrate differently. You can also do number 3. So you can see number 3 right here. we can also do number 4. So you can see how 4 vibrates, 3 vibrates, 2 and 1. So mode shapes are as important as natural frequencies, because depending on which direction it's going to vibrate, you can have, like, say, a little rubber padding or something, that as the part hits that rubber pad, it's going to induce a back frequency which is going to neutralize it. So you can do things with by knowing what the mode shapes are. But anyways, I'm not going to use it on a bridge or something. I just want to tune my guitar string. So I'm more worried about the first natural frequency, and the natural frequency value is 197 Hertz. Right? So there you go. We completed like a modal analysis. Now what's next? Now I need to increase or decrease the natural frequency. So if you want to do that, you are going to have to change something in the tuning fork. Now what are you going to change? Typically it's the length, as the equation that gets solved is this. So let's go. I can just use the brush, I guess. Mx double dot plus Cx dot plus Kx plus D equal to 0. Now M is mass, C is the damping coefficient, K is the stiffness of the part, D is constant, X is the displacement, X dot is the derivative of displacement, first derivative, which gives you velocity, X double dot is the double derivative which gives you acceleration. So this is the equation that it gets to solve when you run modal analysis or any kind of dynamic analysis. So now let's go ahead and find out what will happen if I change a particular dimension. Now you see that you can run different studies. So I'm going to say local sensitivity study. Okay, so I have global and local. Let me explain you the difference between them. So I say local modal analysis. The dimension that I'm going to change here is the length of the tuning fork. All right. So the current value is 10. I want to run an analysis at 8. Okay. So I want to see what will happen if I decrease the length of the tuning fork. So notice that in local sensitivity analysis, I only get to run the analysis at one value, 1 second. So I'm going to run this real quick. It's not as time consuming. Local sensitivities can run relatively quickly. Okay. So what this local sensitivity analysis does is it calculates the modal frequency at 8 minus 1% of 8. 1% of 8 is 0.08. So it's going to run an analysis at 7.92 and 8.08, create a line between them to give you a slope as to, okay, is the modal frequency going to increase or decrease? So you can say, I want to plot the modal frequency, see that, and the first modal frequency when I vary this design variable. So you can see, okay, it runs it at 7.72, you can see that here, and 8.08, and you can see how it kind of like draws a graph. So what it's trying to tell you is the modal frequency is going to increase, or decrease as you increase the value from 7.92 to 8. Okay. So now let's run something called a global sensitivity. In a global sensitivity, you kind of give it a range. So analysis, file, you get to sensitivity study, and here I'm going to say global. I'm going to pick that analysis as a base analysis. I want to change this dimension. I want to change it from 8 to 16. See that? And I want to run it in 5 steps. So what it's going to do is between 8 to 16, it's going to create 5 steps, and it's going to run the modal analysis at each value. So you get a much more accurate, closer solution with a global sensitivity. Now, let's look at the result for global sensitivity. So the measure that I'm going to be worried about is right there, modal frequency. And you can see how it kind of gives you a graph. Okay. Now let's say I want my tuning fork to be close to 150, right? 150. So that's where I want. Okay. So notice that what should be the range of the variable that I have to change? I can change the variable from 11 to 11.5 to 12, right? It's between these two values. Now you see the advantage of a global sensitivity is it will tell you where your answer is. You run the optimization to confirm it. Now if you don't run the global sensitivity and you keep running it between 8 and 7 or 7 and 10, you will never get that value. Also, if you don't run the global sensitivity, you wouldn't know if the value is increasing or decreasing, because the graph could very well be it could very well be like this. Because the graph could have been like that too. You never know. So by running a local sensitivity analysis, it's just going to pick these two values right here and say, hey, you know what, if these values are increasing. But you actually see that by running a global sensitivity, the value fluctuates and it's actually decreasing after here. So global sensitivity is very good. It lets you say, hey, you know what, should I use this value or design variable in my optimization, or if I have to use it, what should be the range? So you see the range needs to be 11.5 to 12, 12.5, I'm sorry. So you go ahead and say, all right, so let's run an optimization. So analysis, file, new optimization, right? So you can say I want to minimize the modal frequency. See that? And I'm tracking a very specific mode. I'm only worried about mode number 1. You can also choose to say mode number 4, for example. So I'm worried about mode number 1, and my limitation is I want the modal frequency of the tuning fork. I can choose a range, or I can say it should be exactly equal to 150. Now, you know, depending on the allowable percentage of error, it could be 150.1 or 149.9 or something like that. Now, what are the design variables? Design variable is this dimension, length. Now, I want it to be from 11.5 to 12.5. Okay. You can also specify an initial value. Do you want to start at 11.5 and go towards 12.5? Do you want to start exactly at 12 and go either ways? You can choose that. All right. So you go ahead, say okay, run an optimization, and you can see the result. So in an optimization, you see real quick, it tells you that this is the value that it found, and notice that it is satisfied within the allowable tolerance, which is 150.13, right? Right? So it does this. It tells you it's reaching that value at 11.78. Now, if I went ahead and say, oh, start from say 8 to say 16, give it a much bigger range, then it will take forever to get there. Okay. So now, once we get that value 11.78, now you can say info optimization history. So you see, do you want to review the next shape? Yes. Do you want to review the next shape? Yes. So you can keep going step by step. and see the shapes. And you can also say, leave the model at optimized shape. You can say yes. Now, as a check, you can really quickly run a modal analysis. And you can see the value, right? So now, a lot of people were asking me about, hey, what else can I do with this? So I can go steel, I can go copy it, go to its properties. One second, I need to create a parameter first. So tools, parameters, add, let's say Young's modulus value and say 200,000. Then I'm going to go back to my material assignment, copy of steel. I'm going to say here I want to insert a parameter E. Okay. See that? So now I'm going to go ahead and rerun this analysis when I change the material property and find out what the value is. You can see right here what the value is. You can run a global sensitivity study, say for example sensitivity design study. I want to use that and I want to vary the parameter E. See that? So I want to vary the value of E from 100,000 to 300,000 in say 5 steps, and I can then get a graph and see, hey, what happens when the value of the Young's modulus changes. So let's say at 235,000 I get my optimum value where the stress and displacement and everything is under control. Then I can say, hey, let's find out a grade of steel that has 235 and we can use that for this particular part. Alright, so let's see, I don't know what I missed here. Did the clicks pretty quick. So you can see as the Young's modulus value changes, you see how the natural frequency changes. Now you can also use it as a part of a stress analysis and see as the Young's modulus changes, how is the stress changing or how is the displacement changing, so on and so forth. Right? So that's what I had for today, where we talked about, like, the process, different buttons in there and what they do, mesh refinement and stuff. We also talked about design studies, local and global, and why we should use them. We spoke a little bit about optimization. I wanted to use this as a the next step after BMX. The next time I'm going to try and present, if I do a Mechanica webinar, would be more or less on say thermal interfaces between different assemblies, more volume and surface regions, some workarounds and stuff like that. Okay, that's what I would plan to do next time within the webinar. So if you guys have any questions, shoot over. I don't see any in particular, but Rosalinda?
Yes, I'm here.
That's pretty much what I had.
Yep. If you find you have some questions after the webinar, feel free to, you can shoot those to me when you get the webinar replay email from me, and I can get those to Sukumar if you don't already have his email address.
Let me just stick my email address in here too. Come on, come on, come on. Alright, is that it, Rosalinda?
That will do it, and I'll have this ready this afternoon for replay on our YouTube page.
Alright, thank you.
Everybody have a great weekend. Thanks.
Bye-bye.